Fine, thank you and welcome. Good morning, good evening, good afternoon to you guys. We are here to run our webinars on isolated versus Zener barriers. So Bob, you can launch the presentation. Before we go on and let Bob talk, let me spend a couple of words about Bob. For those of you who don't know him, Bob is our guest speaker today, and he has over 30 years of experience in the EX world. He's a Comp EX instructor and also an instructor under the ICEX Comp PC scheme. So both scheme he's an instructor of. He's also an he's an inspector, and he's also a member of the US UL STP committee. So meaning he's a very, very qualified person to run our webinar today. Let me try to get control of the request, more control. Here we go. Request, get control of the presentation for a few slides because I need to talk to you a few words about GMI, who we are and what we do and why we do it. Let me see if I have control here. Here we go. So this is GMI, our company. We are a safety company because we manufacture, design, engineer a complete range of intrinsically safe and seal certified devices, which are used in automation packages such as ESD, fire and gas, SCADA, and so on. In most of the industrial sector, primarily oil and gas, but also pharmaceutical, food and bev, and so on. We have over 40 years of experience, and we are very proud to keep our production internally in our headquarters near Milan, Italy. On the other end, we are present in the globe. Because we make safety products, we take special care on manufacturing the same. So we use state-of-the-art technology, both in our product and our facilities. We have 100% product traceability. Every single component that goes in our product is tracked, and we track the testing, which we do 100% of. So every single product has a database with the data recorded onto it. We have an automated manufacturing process, and we are, of course, RoHS and REACH compliant, and we're also SIL3, SC3, so functional safety management certified for manufacturing product up to SIL3, systematic capability. And we try to make very good products because we believe in safety. We believe that a safer product makes a safer environment, so a better world for all of us. These are the products we manufacture, from IS barrier, safety relays with and without line monitoring. We also have isolators, which can be SIL3 certified also. We have power supplies, ATEX, North America certified. We have multiplexers, temperature multiplexers, ARC multiplexer. We have a lot of termination boards that are used to interface with the most common system in the market. We also have a line of surge protection device, or SPD. There's some loop indicators. And of course, we have a division that runs functional safety and EX training and services, which due to COVID in 2020 took, what do we say, Bob? It was put on hold, let's say.
Right.
We are starting again. We are starting soon to run new courses. Now we're trying to do online courses. Let's see if we can manage those. And we are present around the globe. As I said earlier, we have about 10 offices, direct offices. We have 75 distributors. We are about 200 people working in GMI. We run many courses, and we have thousands of installations around the world. These are customers. So system vendors, from ABB to Yokogawa, trying to forget no one. We work with all the EPC, many EPC. We've done several projects with them. And we supply our product onto many machines, skis, compressors, and so on. From the OEM list you can find there. We are also on the AVL of many oil and gas companies around the world. And I believe that was it for the intro on GMI. Now, as I said, Bob is super qualified. Before I let him talk, let me release control here. How do we do that? Give up remote control. Okay, Bob, you're in charge. And there is a box there. It's a question and answer box. You can pose questions throughout the webinar. We will try to answer them during or after the webinars. We also have prepared a presentation with question and answer that were submitted during the registration process. So feel free to ask any question. So far, no, we have run several webinars with Bob, different EX subjects, and nobody has been able to put him in trouble.
Yeah.
To answer questions. So, guys, let's see if you can, pick the best of you. Okay, guys, I'll be here listening and answering your question. Bob,
All
it's
right.
all.
Thank you, Paulo, and good morning, good afternoon, good evening, wherever you're located. We appreciate you joining us. And this was actually one of the first webinars that we did a long time ago, and now we're doing it again. And it's always good to do something a little bit different, and hope all of you are safe during these difficult times. But as Paulo said, we certainly have areas here to you can ask questions as we go along, and we do have some submitted questions that we put some presentation or put a presentation together to answer some of those questions that you've asked ahead of time. So a little bit of review, just real briefly, an explosive atmosphere, hazardous areas, if you will. So our hazardous areas for our conversation with regards to EX equipment is a combination of flammable substances, typically gas vapors or dust, oxygen, and a source of ignition. And when we take that and we put it into a combination, then we can certainly have an explosion. And so when we take electrical equipment or mechanical equipment and we put it into that hazardous area, we need to make sure that that product is compatible and it is certified for that particular environment. So there are different protection concepts that we use with regards to hazardous locations, both mechanical and electrical. So the main ones that we really focus our attention on, or the main ones that you're probably familiar with, are things like flameproof, which is EXD. We see things like EXI, which is intrinsic safety. And then there are other protection concepts as well: EXP, pressurization; O, oil immersion; M, encapsulated, increased safety. So there's a significant number of different protection concepts that are out there. But they basically fall in, if you will, into three major areas. There's what is called segregation, where we segregate, in effect, the flammable mixture from the source of ignition. So that could be encapsulation, oil immersion, or pressurization. So we're removing, in effect, the flammable gas from that triangle. Containment is where we assume we're going to have a flammable air mixture getting in contact with an ignition source, but it will be contained on the inside of, say, for example, a flame-proof enclosure. So that enclosure will not rupture, and it'll allow that hot flaming gas to escape through flame pass and cool off to an extent where it will not ignite the gas surrounding the enclosure. And then, of course, there's also prevention, which both increased safety and intrinsic safety fall within. Increased safety is basically saying, in effect, as long as we have and we meet certain creepage and clearance requirements and we can eliminate the potential for an arc or spark, then that's one protection concept. Intrinsic safety, we're assuming we're going to have an arc or spark, but we're going to keep it at such a low level. It's going to be below the minimum ignition energy curve of the flammable gas air mixture. So that's the concept of intrinsic safety. All of these protection concepts are widely used. There's pros and cons of various different protection concepts, but we'll really focus our attention a little bit on intrinsic safety. So what is intrinsic safety? It is a very flexible and a very cost-effective solution, and it has been around for many, many years. It was actually developed in the mining industry for signaling devices way back in the 1920s. And it has integrated, if you will. It has changed over the years, but the basic premise is fairly similar to what the original rudimentary designs were developed way back early last century. So based upon the ATEX directive, a specific device must be connected between the power source and the field device to make the system safe. So what we call it intrinsically safe barriers, or a barrier. So we use the term loosely. It could reflect an associated apparatus as another term, A Zener barrier or a galvanically isolated barrier is considered to be an intrinsically safe barrier. So what we have there down at the bottom, we have our, on the far left-hand side, we have a simple apparatus, or we can have an IS apparatus. A simple apparatus is basically a device that doesn't store energy. An IS apparatus is an energy storage device. Then we take into account the cables, the interconnects, our associated apparatus that is basically considered to be the barriers, and then our instrumentation circuit that's providing the signal through the associated apparatus out into the field and going back and forth. So again, it is a prevention concept. So it is definitely a low power application. The components that we use on the inside of intrinsically safe barriers are overrated, meaning that they will fail safe in many cases. We also have to have safety factors built into them, either redundancy or based upon those minimum ignition energy curves. We want to keep way below those. There are also some requirements for distances. And of course, we do require the barrier to maintain our system integrity. The applications are basically electronic instruments, measurement control processes, battery supply devices. Anything that we basically can be measuring in many cases or controlling with low voltage instrumentation type products can all be basically made intrinsically safe. The important thing to note is intrinsic safety, while it is widely used, cannot be used for every application. When we get into high power applications, intrinsic safety is not a protection technique. We have to look at different protection techniques. But basically, if we're talking about 1 watt of power or less is more or less our cutoff point where we can start looking at the use of intrinsic safety. So part of intrinsic safety is what is called our intrinsic safety loop. So this is a little more detailed information than what we just showed previously. So again, simple apparatus or IS apparatus with our interconnecting cable, our associated apparatus, our control room instrumentation. Notice on the right-hand side, we have our safe area or non-hazardous area. And then of course, the devices themselves are located within a hazardous location. That does not mean that our associated apparatus cannot be installed in a hazardous location, but we have to take that into account. And in some cases, it is actually a requirement based upon the fact that the distance of our interconnecting cable might be a factor to where there's more storage of energy to where we have to actually locate those associated apparatuses closer to the simple or IS apparatus in the field, which we can talk about a little bit later. But this is our intrinsic safety loop, and we have to have an intrinsic safety loop calculation for every IS installation that we do. So the 2 different types of associated apparatus, there are what are called the Zener barriers. That these are more or less passive devices. They're devices that will sit there. They use Zener diodes to divert a fault condition to ground. And then we have what are called isolated barriers or isolators. Again, another term might be used as a galvanic isolator. So these are active devices that use some sort of safety isolation, and generally some sort of transformer or optocoupler is used on the inside of these isolated barriers to keep that fault energy to pass from a safe to a hazardous location. From a cost, from a maintenance cost, from safety, flexibility, and all this good stuff. Generally speaking, intrinsic safety from a safety standpoint is one of the most safety, one of the highest levels of safety. As a matter of fact, intrinsic safety is actually one of only a handful of protection concepts that can actually be used in a zone 0 environment. It is very flexible because it does allow you to use, in many cases, non-hazardous located electrical equipment, excuse me, within a hazardous location. So in many cases, that installation costs and maintenance costs can be fairly inexpensive. Purging and pressurizing, on the other hand, again, it does have a high level of safety, but there is a fairly significant installation cost in comparison to explosion-proof or flame-proof. But again, every application is unique, so don't use this necessarily as a basis for making your determination. But certainly of the three different protection concepts, these are the three main protection concepts that are widely used, along with increased safety.
Well, and here we
So,
come
Paolo,
to
we have our first poll question. Yeah.
So, guys, let me launch a poll and let's see if you've been listening to Bob. There is no judging here, but what is the basic protection principle of intrinsic safety? It's isolation, mitigation, segregation, prevention, or containment. While our guest answered that question, Bob, there's a live question. Let me ask you. Can you repeat what is increased safety?
Yeah, what increased safety, so this is called EXE, and the concept is basically, if you will, or a good example is where we take a junction box with a bunch of terminal blocks on the inside. Increased safety more or less states that if we have our terminations on the inside of this enclosure separated by certain creepage and clearance requirements, and that these terminals, due to normal operation during in-service, will not loosen up, meaning that they have some sort of a locking mechanism, that as long as we maintain certain creepage and clearance requirements between energized circuits and there's no arcing and sparking going on, then that's the concept, if you will, of increased safety, meaning that now our enclosures that we would use in a hazardous location can be, for example, a sheet metal enclosure or a plastic enclosure. We don't need to use flameproof. So the concept is basically separation of the individual components by distance, and there is no exposed arcing or sparking going on.
No arcing and no sparking. So guys, we've been left to you more than 2 minutes here almost, but I see not a few of you have answered. Any more want to give it a try here? It's not a difficult question. What is the basic principle of IS? Well, let me end the poll. As I said, there is no judging, but just wonder if you will be listening or if we've been clear enough. So a few answer, and of those, 60% were correct, right?
That's correct. Yeah, prevention. So what we're doing again with intrinsic safety is we are in effect preventing an explosion from taking place. And we're doing that by making sure that we're operating below the minimum ignition energy that's required to ignite the flammable gas air mixture. Yeah. So things like isolation, containment are other protection concepts, but in this case, prevention is the right answer.
And well, I'm biased, being sales manager of a company manufacturing intrinsically safe product, but preventing is better than curing.
I sell obviously GMI products, and I'm a big believer in intrinsic safety, but we also provide other products. I will tell you this much, from a inspection standpoint, there are generally many other protection concepts in which we find problems, that it could be designed properly, but yet once it gets installed into the field, if it doesn't get installed properly or whatever, it's very, very, very simple to, in effect, defeat the purpose of some of those other protection concepts.
Although you can also make mistake with IS, and as I
You
think we'll
certainly
be seeing
can.
later.
Yeah.
All right, you go on, Bob.
All right. So a little bit about how these work. So Zener Barriers, the concept, and this applies to all manufacturers that manufacture Zener Barriers. This isn't picking on any particular manufacturer or anything like that. But the concepts is that within a barrier itself, you have three main components. You have a fuse, you have some sort of current limiting resistor. That's generally a wire wound resistor that if the resistor fails, it will fail safe, it will open. And then you generally have voltage limiting Zener diode barrier or Zener diodes. And those Zener diodes, in effect, what happens is that if we have a fault come down or excess voltage, if you will, Zener diodes will basically start opening up and when they start seeing an increase in voltage. When we start seeing an increase of voltage, then the Zener diodes will open up and they will, in effect, shunt that excess energy to ground, what you see over on the right-hand side. Now, if that energy starts going too high, ultimately what will happen is that generally will blow the fuse. So at that particular point in time, our barrier has taken offline. We are not going to get a signal out to our field device. And at that point, we would need to replace the barrier. But we basically have these components that are part of it. And again, that current limiting resistor is a fail-safe, a Zener protection fuse, if you will. When you blow a fuse, it's a fail-safe. The reason why we have multiple Zener barriers in many different products of Zener diode IS barriers is actually, it's a redundancy, if you will, because all these Zeners have been tested and they should all open up at a certain voltage. But if one fails, then we have a backup. If two fails, then we have another backup. So this is actually a double redundant Zener diode barrier, which is a requirement when we're using devices located in a zone 0 area. So we actually have 3 Zener diodes located in a Zener barrier. Now, a galvanically isolated product is very similar. We again have a fuse. We also have Zener diodes. We also have a current limiting resistor, but we've also now included a safety transformer. So this safety transformer, what happens under a fault condition is that we'll have that fault, say, coming from the safe area. Then all of a sudden it hits the transformer, but because it's not directly electrically connected, if you will, that fault will stay within the unprotected side of the IS barrier, if you will. So that's the concept, the big difference between an isolated barrier. Now notice down at the bottom, that fault condition stays into the general non-hazardous area. There is not a requirement for a safety ground with a galvanically isolated barrier. That's really the big difference between a Zener diode type barrier and a galvanically isolated barrier, is the requirement of the safety ground. Now, what can happen under a Zener barrier fault condition? We potentially could bypass either the Zener diodes if the Zener diodes fail, although that's generally not the case. But if we had a fault condition potentially from the safe area connected through that loop, or it's going into the via the loop, if you will, we potentially could create a fault into the hazardous location, basically bypassing the Zener diode itself. So this is something that actually can happen, but we have to make sure that our good ground, if you will, is separate from our normal dirty earth. So it's very important that we don't have some sort of fault condition coming back from earth via the loop into the hazardous area. So this is what happens under a fault condition, potentially under Zener diodes. And again, going back to the fault condition that we have with a galvanically isolated product, our fault condition stays within the non-hazardous area because of the use of the safety transformer. So that's really the main difference between a galvanically isolated and a Zener diode type product. Now, grounding of Zener barriers, if you noticed on our previous slide, what we showed, there is what is called structural ground, and then there is also a clean earth. Generally speaking, what we want to do is that we want to take that clean earth and we want to take that all the way to our system ground. Now, we don't really want to tie it into the structural ground, but at earth, it will be tied into structural ground at some point. But what we do not want to have is that we don't want to have all the noise and all of the potential voltage spikes, everything else that could be existing on structural ground come into, in effect, that safety ground. Notice that our requirement, and this is true no matter if you're following IEC standards or North American standards or standards around the world, the requirements are all the same. We want 1 ohm of resistance or less for our safety ground. So sometimes people will ask, well, how big does that ground conductor need to be? And it could be 4 millimeters squared, it could be 16 millimeters squared. It really just depends on whether or not we achieve 1 ohm resistance or less for our safety ground. The reason why you will typically find in many cases a redundant safety ground is that there is a requirement to periodically check to see the resistance on our safety ground. So what we would in effect do is actually have 2 connection points. We would remove one, make a connection point, test that ground, reconnect it, and then test the other one to make sure that we are truly achieving 1 ohm resistance or less. Now, this is again an issue with the Zener barriers on the independent grounding, because if we have a situation where it is tied into our structural ground, then we could potentially have a fault condition coming back into the barrier itself or working its way into the field device via the structural ground. So it is really important that when we use Zener barrier products that we make sure that that structural ground in effect is separate from our normal earth, our dirty earth versus clean earth. This is the inspection schedule that you will find in the IEC 60079-17. And actually, we have now adopted this in the United States as a UL standard. And this just is telling us the specific requirements that we do, and that we actually do have to go and make an earth continuity check for non-galvanically isolated circuits. So is the insulation resistance satisfactory? Is the earthing satisfactory? This is part of our detailed inspection when we bring products in IS loops into service, and is a requirement under the -17 standard. So it's not just me telling you this, this is actually written in the standards and is part of the requirements when we do use IS circuits, and specifically these are the ones that would apply to a non-galvanically isolated system. So people ask, so therefore I'm telling you all this great and wonderful stuff about galvanically isolated versus Zeners, right? Well, there are some trade-offs, right? There's cost benefit analysis. So as I mentioned, the largest advantage for using a galvanically isolated barrier is the requirement to not have that safety ground. So that can be a significant cost savings, and certainly all the maintenance that is required in ensuring that we do have a good ground. Generally, we have very good accuracy. And again, it allows the use of grounded or poorly isolated sensors. So Zeners, again, we do have to have that dedicated safety ground. It does require routine checks. There is a potential on Zener leakage accuracy, but it's not a huge issue, but it can be an issue. So those are basically kind of the pros and cons, if you will, on galvanically isolated. Now, the big question usually comes up is, well, what about cost? You know, what is it? How much does a galvanically isolated product cost versus a Zener barrier? Generally speaking, the cost for the barrier itself, Zener barriers are generally going to be less expensive because, in effect, we don't have to have a transformer in there. We still require the current limiting transformer, the fuse, and the Zener diodes, although the Zener diodes on a galvanically isolated barrier are generally smaller than what you would find on a Zener diode barrier. But generally speaking, what has happened over the years, as more and more people and shifted away from Zener barriers, going more towards galvanically isolated products, the cost differential has come down significantly. So nowadays, you are finding that the actual cost of a product versus product A versus product B is not as significant. And then when you start adding in the cost of the safety ground and all that other good stuff, then you start finding galvanically isolated products in many cases are much more cost-effective means to go.
Especially when you have, you require two barriers on 2 wires. So we have another poll, guys. Let me launch this poll. As we said, just give us your answer. It's a little more than before. We want to see more answers. But while our guest, our answering this simple question: is a dedicated low-resistant ground required for galvanically isolated barrier installation? It's a very easy answer because Bob has been talking about this for a little bit now. I do have a question which I answered by typing. I've been typing away some answer while you talk. I want to make sure I didn't do a mistake. I'm pretty sure it was about we require a grounding for Zener barrier less than 1 ohm. That 1 ohm is from the farthest barrier to the peak ground, right? The complete line.
Correct. Correct.
That's what I answered, but I wasn't the percentage.
Yeah.
It was 99.9%. I
Yeah.
did also provide some other answer. I hope there is some question about junction boxes and IS boxes later in the question and answer. We can go through that. We have
Yeah.
had a lot of discussion about certification of IS boxes and not in our previous webinar. We can do this a little bit later. Okay, now we have a few more of you have voted. Let me end the polling. And most of you have answered correctly. Not.
You guys were paying attention.
Yeah, you've been paying attention. So basically for a galvanically isolated or an isolated barrier, there is no grounding requirement, whereas there is a grounding requirement for Zener barrier, and there has to be less than 1 ohm. So, okay.
That is correct.
You quit the poll. Okay, so you can continue. And I
All
prepare
right.
for the next one.
Yeah, we'll bring up. So that was very short and sweet.
Yeah, it was quite short this week. So you guys will have more time. Now we go into the, so let me get out of here, otherwise I lose control. Okay, great. So let's go. We have had a lot of questions through the registration process. We put together some answers. We will also discuss live question, as we just got one that said about why we do not have an IS certified enclosure. We use IXE enclosure, right?
That's correct. Yeah. Generally speaking, the requirements are for intrinsic safety junction boxes, if you will. We had this question actually, if it's a single circuit per the IEC standard, the -14 installation standard, it actually does not require for a single circuit that the box be certified. However, it has to meet the impact resistant requirements and all this other good stuff. But let's assume that you have multiple circuits going into a junction box that's housing IS circuits. The junction box, actually what is typically used is an EXE enclosure. The requirement actually states that the box must be certified to meet the requirements of 60079-0, and it must be labeled as contains intrinsically safe circuits. So that's why people typically would use an EXE box and then just put a blue label on it says this box or this enclosure contains intrinsically safe terminals. That doesn't mean you couldn't use a flame-proof box if you wanted to for some particular reason. You could use a flame-proof box. But generally speaking, the most common methodology is going with an increased safety box, because you typically were not going to find a junction box that's rated IS, if you will.
And for example, our IS product, like a barrier, will have an X at the certificate end, which means there are some requirement. And one of the requirements is, for example, to install the device in an IP54 enclosure, because itself, a barrier is IP20, not suitable for installation,
Correct.
outside. So, okay, let's go to our question and answer. Let's see the first question we got. Let me close this down, otherwise I cannot read it. Multiple barrier wired in series and parallel. That's a tough question, Bob. Can you remember who posed this question, but it was very recent in this very registration. And it does happen. Sometimes, for example, on a DO barrier, you're trying to power a solenoid valve and just don't have enough juice to pass through the barrier. So you can put channels in parallel to increase power delivery, but at the same time you increase safety parameters, so you need to take that into account. And I know you put down a lot of reply. You let me know when I need to, or if you want to take control of the screen, is the same.
Sure. Yeah. Well, I tell you what, why don't you give me control? Let's see if I do have control. Yeah. Why don't you give me control? I guess, can I request remote.
Yeah. Okay, approve. So you're on in charge now.
All right, so this is straight out of the Dash 14 standard is the design and installation standard in the IEC world. We have within the North America, we have the NEC code book. We also have an ISA document. We have a bunch of different documents, and the CEC has theirs. In the international community, we follow Dash 14, and there's some other standards in the IEC world, the Dash 25 standard as well. But basically, we take into account both the voltage and the current, and this probably will show you a little bit better if I can. See if I can advance this. Can I advance it?
If you cannot, I will do it for you, Bob. Here we go.
Yeah, go ahead.
Next
Go ahead. So this is a typical installation, associated apparatus single supply, where our voltage in this case is 28 volts, and we have 93 milliamps coming out, right? And then if we go to our next slide. So if we do a series connection, basically what we're doing, we're doubling the voltage, if you will, but the current output is basically the same. Then if we go to the next slide, if we do two supplies, parallel connection, right? Now our voltage goes back to 28 volts, but the power is now gone up to 186 milliamps. So this might be a situation like you just mentioned, Paulo, where you need more power. So you might do a parallel connection with two different associated apparatus wired in parallel. This is what we would take into account. And then I think the third one is series and parallel. So in this case, we're taking two different associated apparatus and wiring them directly into that piece of intrinsically safe equipment. And so we have basically doubled in effect. So these are all part of what we would call the entity parameters that we need to do our calculations to make sure that we are below those minimum ignition energy curves, depending on the gas groups, which we're going to talk about here in just a little bit as well.
Is it? Okay, Bob, great. So basically you need to recalculate your safety parameters if you start playing with more than one barrier into the same IS device.
That's right. That's all we're doing. So we just double it.
For example, if you take in our case, we have multiple channel barriers that you can basically play with and create combination of channels. And in doing so, we have already taken that into account. So we are giving you parameters for the different combination, channel A plus A, A plus B, B plus C, and so on. But
that's right.
I remember something else. If there was, if you're using those two different barriers, there's some kind of drop in, some limitation applies.
There is, and I can't remember it either.
There is something, but anyhow, remember, I will check into that. Okay, now next question is again about entity concepts. So we talked about, calculations. It all implies that we know what it is, an entity concept, and how we do this calculation. So prepare some answer on that.
Right.
Entity versus system approach.
Right. So generally speaking, most people use the entity concept where we're more or less as designers, engineers, we're taking a end device and we're taking our output from our control panel, and we need to match, in effect, the associated apparatus along with the cabling as a complete, to turn it into, in effect, the system approach. Now, entity concepts, we have to, first off, we need to understand what is our associated apparatus. Well, not so much the associated apparatus, but we need to know what the end device is. And we basically say, okay, the simple device is more or less like what we talked about before. A simple device does not require certification, and more or less it's just a device that does not generate or store energy. So things like an RTD, a switch, resistor, a simple semiconductor, those are all simple devices. Now, when we get into IS apparatus, those devices do require certification, and these are devices that can store energy. So these products will actually be marked EXI, and they will give you the entity parameters associated with that particular device. And these could be things like transmitters. Yes, yeah. Here's a great example, right? So our associated apparatus, which is the barriers, we're going to have this type of information by the manufacturer. So what's the maximum allowed voltage? I won't read through all of this good stuff, but our EX verification down there at the bottom is basically what the verification tools will do. So we want to make sure our voltage output doesn't exceed the input to the device, the power output doesn't exceed the power input, so forth and so on. Now you'll also see COLO, and that's our capacitance and inductance. So we also have to take into account the capacitance and the inductance, if you will, from the cabling. So we take that as well, and we add that all together and make sure that we're below the parameters. So these are our entity parameters, and this is what we do in order to generate, in effect, our loop calculations and ultimately generate our loop drawing.
Yes, and if we, it looks a little complicated, and it is in a sense. So we have for GMI product, you can go online, use our EX loop safety parameter verification. You enter this data, the barriers data by selecting the right model are automatically pulled up, and you get something like this. You get the sheet that you call well, it's part of a DSD, right?
DSD, that's correct. Yeah. So it's
and you get some example. We have some example here, and basically at the end you get different. It also matters which gas group you're going to use it, because different gas group have different safety parameters.
Yeah, and if Paulo, if you go back to the previous slide,
yeah,
that's probably that one right there. That's a real good example right there, the difference. So what you see on the left-hand side and what you've circled down at the bottom, you see there's 677 meters, right?
Yeah.
And on the right-hand side, you see 5,770 meters. So what's the difference? Well, basically, if we look real close in there somewhere, the parameters that we see on the right-hand side, on the column on the right-hand side, are actually for gas groups 2B gases, while the ones on the left-hand side are for 2C gases. Now, if you're familiar with the particular gases in those areas, 2C gases are gases such as acetylene and hydrogen. They have very, very low minimum ignition energy curves, meaning it doesn't take an awful lot to ignite those gases, where 2B gases typically have a higher level of energy required. So what that's basically telling you there is that if we're going to put it into an environment in which acetylene or hydrogen is present, a 2C environment, notice that the length of cable run based upon the capacitance and the inductance is much, much less than what we can do for normal 2B or even 2A gases. So it's important to understand when we're doing our calculations to understand the gas group, because the cable length will play a major factor. Now, for many applications, many people don't have a huge issue with this because they may have the control panel located within 50 meters or 100 meters of the end device. But if we're in a big refinery or a big processing plant, sometimes this can be a very much a limiting factor. So we have to take that into account.
And we have used an example here, super good cable. Typically the numbers come out smaller when you use a different cable. We do have a question. I don't know the correct answer, but I believe, we ask, what about 3 wires loop? We are giving safety parameter also for 3 wires loop. I guess the cable, and the question is about inductance or impedance. I would imagine you have to use those that are provided by the 3-wire cable manufacturer.
That would be correct, yeah.
I don't believe there's any difference between 2 wires or 3 wires or.
No.
Okay,
no, we would.
Yeah.
And there was another question there, I think, encounter multiple barriers into different segments, each barrier in each segment in a loop. Do you know how we do the IS calculation? So in that one, you would treat them all as individual loops. Now, if there's multiple barriers in that same loop, kind of like what we showed on those examples at the very, very beginning, then certainly we would show those on our DSD. So we'd have a wiring diagram. We'd also, within our DSD, show the barriers themselves, and then we would do the calculations and we would show that on the drawing as well. So I don't know if that answered the question or not, but hopefully it did. So.
Okay, well, let's move forward. We still have 15 minutes. So, at the end, there's always a big debate over isolator and Zener barrier. And the big question is it matter of, we discussed grounding. Grounding is the big difference between the two. One requires, one does not.
Right.
Is there any other differences or any other issues? So we prepare an answer here. There are some other differences.
Yep.
Pros and cons.
Yeah, and by the way, for anybody who has any specific applications that you are curious about, feel free to send that to us. We'd be happy to do some of those calculations for you. Again, you can go online, you can go to the GMI website, or you can drop Paulo or myself an email, and we'll be happy to double check your work, take a look at it. Or if you just need us to do a quick loop calculation, we can do that as well. So don't panic. don't freak out. We'd be happy to help.
Well, but basically, to try to summarize it, there is a cost comparison. You mentioned earlier that Zener barriers are less expensive. Typically, they are. But when you take into account, for example, some application which we did recently require 2 Zener barriers on the 2 wires, you cannot use a single Zener barrier. Well, then the price becomes, significantly not so significant. In fact, it can be more expensive to use a Zener barrier. Then you have we also
the multi-channel barrier.
Multi-channel lower the cost of isolated barrier drastically because you have a single power supply for more than one channel. What else we are talking about here?
Well, one thing that's not on this slide, Paulo, is, and I think this is an important consideration. Generally, as we talked about with galvanically isolated barriers, we have to introduce a transformer on the inside of a barrier, right? Yeah. So generally speaking, the first generation galvanically isolated barriers were much wider. As a matter of fact, the first generation GMI products were about 25 mil, I believe. So the next generation, what's happened is that manufacturers have been able to basically make their galvanically isolated barriers much thinner. And so therefore the stacking density, where Zener barriers used to have a big advantage on stacking density, that has somewhat gone away, because galvanically isolated now products, you'll actually find that the thickness, if you will, the density to be able to mount on a DIN rail has shrunk significantly. So that used to be a big advantage on Zener barriers, and it really isn't.
Because the Zener barrier, it has been the same since its conception. It requires big Zener diode, it requires a fuse, it requires a certain kind of resistor, which voluminous needs to be potted. So they have not changed in the years, whereas electronic has taken drastic change in the last 20 to 30 years. So an isolated barrier used to be as big as a A4 sheet or a legal letter. Now it is 10 millimeter wide. All right. So the question is about how do I connect safety ground or Zener barrier? Well, we have only a question about if it has to be less than 1 ohm. Yes. And how do I connect it? Here's some example.
Right. Well, we kind of covered the information on the left-hand side, but on the right-hand side is actually showing a specific mounting of a Zener barrier to a DIN rail. One thing that when we do inspections, and I've seen this quite a bit, where people will mount Zener barriers directly to the DIN rail, and that DIN rail is mounted directly to the enclosure via metal standoffs, which in turn is connected to dirty earth. So it's really important that if we do use Zener barriers and we're mounting them to DIN rails, make sure that that DIN rail is isolated by the use of isolator standoffs, if you will, from the enclosure, assuming the enclosure is a metallic enclosure. Do something to make sure that it is isolated from the enclosure, because again, that's going to be tied into your dirty earth. So that is a typical installation where you might find the Zener barrier mounted to a DIN rail, which in turn is tied into a ground conductor, and that is your clean earth that's going to be tied into your clean earth. So it can be done in that fashion, but a lot of Zener barriers will also have earth tabs on the outside, like what you see on that right-hand picture, and you can make that
I was
connection
trying to
directly in.
annotate here, but I guess I cannot. I don't know how, but anyhow, it is showing there somewhere. It's because I have it on the second screen. Did you see my mouse or not?
I see it. I see it.
Okay,
Yep.
so I have to move to the next screen. All right, next question. Do I have to keep the IS and non-IS wiring separated for isolator or for bare? And this is, the only real issue you can encounter in IS application. Here are some examples, of course,
Yes.
that we do.
And this holds true for either Zener or galvanically isolated. So it doesn't matter. Either one, you have to maintain separation between IS and non-IS. So
It is very important to do so because you can defeat the purpose of having a barrier.
Right.
And so we are actually going to ask a question, guys. Let me see if I can do that.
And I don't think we covered this in this.
No,
we didn't
did not
give
cover it yet. So we said it has to be isolated. The question is how much? Do you know the numbers, guys? Do you know what is the distance requirement between an IS and non-IS circuit? It's a number. It's either 25 mm, 40 mm, 50 mm, or 80 mm. Mm stands for millimeters. It's a number you should, if you work with IS, you know it by heart because it comes across all the time. I see your answer coming in. Most of them are not correct, but it's okay. We're not judging. More, just for a number there, you have 1 out of 4, so you can 25% chance of getting it right, even if you don't know the answer. But it's very important to keep segregation because, for example, you might have a high power trunk, non-IS wiring, with high voltages in there. You might have a short somewhere, the wires could melt down. If connected wire next to an IS circuit, you will melt those wires and you bring in very high voltages down into the hazardous area.
There's ways of getting around that segregation distance as well, which by shielding the cables, by using armor, there's different ways that we can get around doing it. But if we're using unarmored conductors, cables, we do need to
in the
make
same cable trays or in the same enclosures.
Right.
Well, I hand the poll here and I see it's mixed answer, but the right answer is, Bob?
C, 50 millimeters or 2 inches.
50 mm, yes. 50 millimeters is the required distance between IS and non-IS circuit. So let's share this result so you guys can see it. You have a mixed answer here. Some 50, some 40, 25. 25 is too short, not enough.
That's right.
Okay, stop share result. Let me show you some example here of what it looks like a good and not a good installation. These are bad installations, right? Well,
so yeah, what you see on the left-hand side, you see, and generally speaking on your IS, you're going to see blue on one side of your IS barrier, regardless if it's galvanic or Zener. That's going to give you visual indication that that's your intrinsically safe side. But what has happened in that situation is that somebody has run the cables all around that in those IS barriers to where we've now defeated that 50 mil separation between IS and non-IS. The same thing holds true up on the panel that you see in the top right. You see the same thing. It looks good from the outside, right? We have IS cables on the right-hand side. Looks like non-IS cables on the left-hand side. But then as soon as we open it up, we have all these loops and bunches and everything else. The picture on the right-hand side, you actually see there is a partition between your IS barrier, right, where you have your mouse there, where you did have it there, Paulo.
well, I was trying to get to a different type of drawing, something that I can show you better. Here's a partition.
Yeah, that's it. That's it right there. They put a partition in, which is great. But then the problem was when they did the installation, then they looped those IS cables right next to the power cables. So they have some bundled there, right? That's one issue. And then the other issue, if you look at the bottom, it looks like a contactor of some sort with that L1 connection. And then right next to it is some conductors leaving, going out to a field device, and we've defeated that 50 mil separation. So that's definitely an issue.
Definitely an issue. Okay, let's clear this and move on. Clear all drawings. Let's move to the next question. What about using Zener barrier with grounded sensor? This is another issue. I don't know if we discussed this earlier, but there is another limitation when using Zener barrier, which is grounded sensor. You can actually not use a Zener barrier with grounded sensor because you would have two ground paths, as shown in this slide.
Right. And we kind of talked about this a little bit earlier, but yeah, that's
okay, good. So yeah, because then there's a leg of the fault can go down this leg, one of the two legs, and you will not have control on it. Coming back to another question which we answered live a little bit earlier was, can I install a barrier in a classified area, zone 1 or zone 2? Well, not the same question we got earlier, but in a way, yes, you can, using the proper enclosure.
right. So many barriers, for example, if you look at the GMI range of products, they're actually dual marked, if you will, from an EX perspective. They'll be marked as an associated apparatus providing protection downstream, but they'll also be marked of where they can actually be located. And so GMI's product is actually certified EXEC, or the old protection concept EXNA, which is non-arcing. So the barriers themselves are actually suitable to be mounted in a zone 2 environment. However, we might need to put them in a zone 1 area. Maybe that cable run, we have to keep it much closer than what we thought. Then we would have to take those barriers and potentially install them inside of a flame-proof enclosure, or on the case of the right-hand side, we might install it inside of some sort of pressurized EXP enclosure. So there are different ways. Sometimes we can just take them and install them obviously in a safe area and we have no issues. But in other cases, we do need to install them in a hazardous location. And so we just have to look at the marking on the barrier itself, figure out what it's suitable to be protected in and of itself, if any. And if it's not, then we have to use some other protection concept to mount those associated apparatuses inside.
Yeah, and we had a whole webinar the other week on marking how the barriers or apparatus in general, EX apparatus, can be marked, and you guys can go look it up back online. We have recorded. It is worth looking into it. Marking can be complicated, but it's the only way. Okay, right. So should I worry about seal on an IS barrier? Question came in from a registration process. I guess so. It's not a requirement. Nobody says the barrier needs to be seal certified unless it's a specification of safety system, functional safety requirement. But in a sense, the seal certification does provide for a little better product, no?
Yeah, it does. And here's the thing. In order to achieve a SIL rating on a particular component, whether or not it's a valve, whether or not it's an intrinsically safe barrier or a PLC or whatever it is, there has to be a tremendous amount of traceability of all the individual components, and there has to be calculations as far as failure modes, when they are going to fail, all of this documentation. So all the components, when you build an intrinsically safe barrier that actually has a SIL rating, if you will, that means that everything that goes inside of that barrier has gone through a significant amount of data and testing to be able to determine how this product will operate over a long period of time. So in effect, what you're basically paying for in this scenario is reliability. It's telling you that this product will last X amount of years, and we can achieve a 99.99 or whatever that percentage is, depending on the SIL loop, functionality and safety. So it kind of goes hand in hand to the concept of intrinsic safety, but it's like just an extra step. It's telling you in effect that this product will last for a very long period of time.
Yeah, and as a matter of fact, today all the barriers that I know, all the manufacturers have minimum SIL2 rating. Some have SIL3, like ourselves, but we'll have SIL2 anyhow. It comes basically with it, because you need to design the barrier in any case, to a high degree standard, because it's a safety barrier. So it has a lot of requirement anyhow. So
Right.
again, we have a question about if isolators are the mainstream today. When can is there a situation when I need to use a Zener barrier, or for example, driving a high current? And okay, well, we have an answer for that. When isolator or Zener barrier can be used, of course, I don't know if we discussed this earlier. An isolated barrier is designed for a specific application. So an analog input, analog output, digital input, digital output, vibration. I don't know. I can think speed.
Right.
Magnetic pickup or something. So they are dedicated. So in some cases, you might find a sensor out there that the barrier was never designed for it. So a Zener barrier will solve the problem because it's only a passive device. It doesn't do anything to the loop.
Right. Yeah. Just remember, Zener barriers are direct wired, right? So whatever that signal is, whatever you're getting from the field is going straight back. There is nothing there to disrupt it or change it or do anything else. A galvanically isolated barrier is a transformer. So it is taking a signal, transforming it back.
And we had a question earlier, which I typed and answered. I guess everybody read it. How with this signal is passed through the transformer. There is ways, we use analog to digital converter. So we make the signal in a digital way and pass it through the transformer. And there's some technology behind it. We cannot disclose all information.
And it's magic.
It is possible. Yeah. Basically, a galvanically isolated barrier uses a transformer to isolate anything between the hazardous area and the safe area. So you're talking whether it's the signal, the power, isolation to the power supply, to the signal, to the different channels. Sometimes you have more channels, so you need to isolate the channel to channel. Okay, well, let's see. We are coming to the end of our time. In fact, we passed that. There are a few more questions. Can you explain the conformance of Zener and isolated barrier? Is there any difference? Well,
I think we kind of covered this
several times. Basically, it's grounding, right, Bob?
Yeah. Yeah.
One requires grounding, one does not require grounding. But as far as installation, as we saw this earlier, it is basically the same.
Correct.
What about question about functional safety? Well, guys, we are running many live webinars and we have recorded many webinars. So you can look from our website and see our live webinar schedule or the earlier run webinars on YouTube channels. And you can see we are running webinars on application oriented, functional safety, EX, at least 20 different subjects. You can find them on our website. So we come to the end. Let me see if I can do this. Share our poll, our last poll, guys. Give Bob launch poll. Here we go. See how Bob did, because I always mess it up. Okay,
well,
great.
I should have no excuses this time because this was in the middle of the morning for me. This is fantastic.
Yeah, normally we run webinars for you in very early morning or very late evening. Today was, midday, so you are 100% on top. In fact, we run very smooth. We are ahead of our normal time. We normally run very late. Today we did very good. Also because you guys didn't pose too many questions. There's still a few moments if you want, but okay, great. Most of your answers are in. Let me end the poll here so you can see the results, share the result. Let me go to the last slide. So you have our contact details there. All right, thank you for the, you closed the poll, Bob? Yes?
I did.
Okay, great. So thank you. There's no more questions. Thank you. Thank you again, Bob. Thank you for your sharing your knowledge with us today.
My pleasure.
See you soon. Next time, I believe is in a few weeks, a couple of weeks.
Yep.
And enjoy the rest of the day. Thank you guys for being in with us. Any question, just type to us, okay? Type a question. As Bob said, you can answer, you can ask questions throughout your email. Thank you again, Bob.
Thank you. Thank you, Bob.
And See you soon, guys.
Ciao.
Ciao, ciao, ciao.